So I'm just going to show you adding vectors here. You might remember this picture from, oh, it's not going to show it. You might remember this picture where the plane goes like this, and then sometimes when the wind is like this, it slows it down, and when the wind is to the side, it goes like that, right? Because I think for the most part, you guys all understand vector addition, that whole tip to tail thing, right? Okay. So now remember, we don't need to do that. In grade 11, we added two types of vectors. We did them at right angles to each other, and we did that by Pythagoras, right? So if you've got like 6 here and 8 here, then that's going to be 6 squared plus 8 squared, and then you take the square root of it, right? You guys have done that something, right? If it's not at a right angle to each other, then you had to do it by scale drawing, and then you would get your ruler and your protractor out, and you would do that kind of thing. You probably remember that from grade 11. Okay? So if I asked you to do this question, and it's on that sheet there that I just handed to you, and when the guys show up tomorrow, you can give this to them. If you had this 3-vector one, you would have to do it by scale drawing, right? Now what I showed you yesterday was that there's this idea of the component. So we could take that one there, and that one there, right? This one here only has a left-right component. It doesn't have an up-down. And then this one here, I'll draw in black, would be like that. And like that, and I'm just going to, just for the sake of things, I'm going to make this one in blue. If I were to add all the x and y components together, if I were to do this, oh, I've got to do them separate. That's separate. Can I ungroup? Ungroup. Okay, so I'm going to go left, right, and then I'm going to add this one, tip to tail, and then I'm going to put the black one, oh, I got to ungroup that one. Ungroup, and I'm going to put this one tip to tail as well, right? So my total, I'm going to have to move everything over to the right. Red, blue, black. So my total one is from, let me see if I can get a different color here, green. The total one is, I started at the red, so that would be my total x vector, right? Does that make sense, Kalen? That's the sum of all the x ones. Now, if I take all the y ones together, that's this one here, and I just keep adding, right? I add that one on there. There's no y from this one. This y1 is right here. I put it tip to tail, right? And so the final y is, in green, from there. Whoops, that's a terrible line, but you get the idea. Straight down, right? Now, if I'm going to do this, let me just see if I can do it. Dotted line, where did I start? I started right there. That there is the overall result. And in fact, if I take that pink and I put it right there, look at that. Same value. Does that make sense? When I added them by scale, I went there, there, and there, and I drew from there to there. And when I added by components, I ended up with exactly the same vector. And that's really the concept that we're doing here, except we're not going to draw all these by scale. We're going to actually use math to find them, and we're going to add them numerically. Let me show you. Okay? So here's the first one, and you should have this on your paper here, right? This is equal to, whoopsie, this is equal to this vector right here. I'm going to add these 3 vectors together. So this one here, example 1 by components. Okay, so D1 is 0.5 kilometers at north, 20 east. So this is 20 kilometers, no, not 20, 0.5, sorry. 0.5, and it's north, 20 east, right? D1x here, the x is opposite, so it's going to be the sine. 0.5 sine 20 is 0.17. And the adjacent is the cosine, so it's 0.5 times the cosine of 20, or 0.47. Have I gone too far, or are we good to there? Both of these are positive because they are up and to the right, so both of them are positive. So what I've really done there is I figured out how long, when we did it back here, I figured out how long, it was the red ones, right? I just did that one, no, the red one. I just figured out that's the x and that's the y, right? I think I actually had them, sorry, I had them like this on the diagram, didn't I? Does it matter whether they're like that? Is that okay? Yeah, that's fine. Okay, so I figured out the red ones there, and those are numerically equal to 0.17 and 0.47. Let's do it for the second vector. The second one is straight to the left. Tony has a question.
Is this just like under the more method, or is this like outside kind of thing?
No, this is now right here on the sheet that you guys.
It is on a.
Yeah. Oh yeah. Yeah. So the second one is 0.3 kilometers. Is it 0.3? Yeah, 0.3 kilometers, and it's straight west, right? So the x component is minus 0.3. Why is it minus? It's to the left. It's 0.3 because all of that 0.3 is west, right? Is there a y component here? Is there any up and down? There is not. So the y component is 0. Does that make sense, Lindsay? Yeah? Garrett, good? Okay, so let's do the third one. The third one is 0.8 at west 50 south. West 50 south, like that. The x is adjacent, so it's going to be 0.8 cos 50, and because it's to the left, it's negative 0.51. And the y is down, it's 0.8 sine 50, sine because it's opposite, minus 0.61. Down is negative. And here's the neat part. I'll pause for a second, yeah. Okay, so this is the neat part here. The next step is to simply, and if you flip your page over, it says in the back there, add all the east, west, or x components. So I take what I like to call Rx, the x component of the resultant, is equal to the x component of displacement 1, the x component of displacement 2, and the x component of displacement 3. You're adding all the x components together, exactly like I did graphically way back here. Remember when I took all the x's and put them all together? Right? Numerically, right? It'd be something like that, I think. Sorry. So take all the x components and add them together. 0.17 plus minus 0.3 plus minus 0.51. Are the negative signs important here? But does it matter? What does the negative sign mean? That it's going left, right? So does it matter, Tony, whether it's left or right? Yeah, it's huge, right? It would be like me drawing this arrow, this vector. Whoops, went too far. It'd be like me drawing this blue one, or the green one, that way. And that would clearly be wrong, wouldn't it, right? Don't do that. So yes, that's important. You must include the signs here. Okay, so we're going to add up all the x's. That's my x component of the result. The next step is to add all the north-south or y components. The y component of the resultant is the y component of vector 1 plus the y component of vector 2 plus the y component of vector 3. Again, making sure you've got your signs. Okay, so now what we do is we take the x component and the y component and we add them together. Again, very much like I did back on this slide here when I put all the x's left and right, I put all the y's together, and then I ended up with a right triangle, and I ended up with that pink hypotenuse. So, same idea here, right? X is to the left, minus 0.64, the y is down, minus 0.14, and now because it's a right triangle, you can use Pythagoras to solve it. Is this component of sum of the resultant, the x and y, is it always going to be a 90-degree triangle? Yes, it is, Tony. Excellent choice. It has to be, because these are all the x's which are left and right, and these are all the y's which are up and down. They have to be perpendicular. You have to end up with a Pythagorean right triangle at the end here. So it's a fairly simple matter here. Minus 0.64, 0.14. Do the signs matter here now? Not a whole lot, right? Not in the numerical answer anyways. So you come up with 0.66 kilometers. And because of the angle here, because of the direction, it's going to be opposite minus 0.14 all over the adjacent 0.64. Second function tan, it's 12 degrees, and that's going to be west, right? 12 degrees south. So really, we haven't done a whole lot new here. We've just taken bits and pieces of things that you already know and sort of put it all together in a mathematical strategy, I guess you could say. All right, so let's just sort of go back and come up with, like, what would be the steps? Like, if you had to write down the steps to do it, what would you say they would be? And I would suggest you, here, well, let's look at the cartoon first. That's good, isn't it? Yeah. If you had to write down the steps, what would you say they would be? What would be step one? Well, let's be more generic. Let's be more sort of, right, so it can work for every situation, right? I would say something like, you want me to write them in here? I'll put them in blue. What's step one? Find x and y components of first vector. Would you agree that's a good step? Does that describe it? Find the x and y components of the first vector. Right? What would you say is next? Find x and y components for basically any other vectors, right? In fact, you could just write the step as find x and y components for all vectors, I guess, couldn't you, right? Then do what? Add all x components. Add all y components. Right? And once you've added all the x and y components, then add Rx and Ry by Pythagoras. Right? And then do what? Find your angle. Is it a good idea, do you think, to draw this picture? Yeah, probably. Right? You pretty much need that picture to help you with the angle. It's not impossible, but it's certainly a lot easier if you know that the minus 0.64 is left. Like, it's a whole lot easier coming up with west and south if you've got that picture, right? So once again, yeah, your steps are pretty easy, right? Find your x and y components for all the vectors. Add all the x components, call them Rx, resultant x. Add all the y components, call them resultant y. And add them, find the angle. When you put it that way, it's pretty simple. 0 degrees. Okay, I'll be quiet now. I don't want to go do too much today. You have the sheet you did yesterday says vector components on the front where you just have to find the components. You should probably try the vector addition ones here on the back side. I know the solutions are in the white binder. There's a QR code on the back that you can scan to see those as well. Try these tomorrow if you can. Show people tomorrow. If they have to watch the video, that's fine. I'll reconvene on Monday and we'll see where we're at. I'm going to do a little foreshadowing here. If I asked you to subtract vectors, what would you do? Like if I had to take...
Everything except instead of adding, subtract.
Exactly. Makes subtraction a whole lot easier, doesn't it?
Perfect.
Instead of adding them, you subtract them. So yeah, pretty easy. All right, time to be quiet.